Um, if you haven't mastered 5.2, then I think 5.3 might be a little bit confusing. So let me kind of refresh where we are with the volume stuff. Basically, at this point, you could think of it as in two different camps. In one camp, we're doing what was something we call cross-sectional areas. In the other camp, this is 5.2. And then the other camp is 5.3, and that's cylindrical shells. And the key thing with 5.2 is we chop up perpendicular. So this symbol means perpendicular, it means like at a right angle, perpendicular to the axis of rotation. Okay, so this basically breaks down into two types. One type is a disc, and the other type is a washer. For the disc one, the formula is the integral from a to b pi times the radius squared dx. And for a washer, the formula is the integral from a to b pi times r big, that's the bigger radius, squared minus pi times r small, the smaller radius squared. So this is really just the area of a circle times a little bit of thickness, and then you add up all those discs together. This is really a big circle, area of a big circle minus area of a small circle. So then you get like a little washer thing, and then you add up all the volumes of all the washers together. Okay. So if we would draw a picture, the washer picture kind of looks like this. And the distance from here to here is r small. The distance from here to here is r big. On this other side, this picture looks something like this. This is this much simpler case. This is just r. The idea is that each of these things will depend on x possibly, and x ranges from a to b. We can do the same thing with y values. So I'm not going to write those formulas down. Now that I've said all of that, that was all earlier stuff. So what we want to do now is we want to look at cylindrical coordinates. And the reason why I really emphasize that you master the washers and discs first is because when we talk about the cylindrical shells, we chop up parallel to the axis of rotation. So this one is not using cross-sectional areas. This one is using shells. Let's take a look at this guy. Let R be the region between the graph and the x-axis over this interval from 0 to 2. So we can draw a set of axes like this. Here's 0. Here's 2. Does anybody know what kind of object this is? Is this a line? Is this a parabola? Is this a cubic function? Is this a square root function? Is this a rational function, radical function? It's a parabola. And then when you think about it, does it open upwards or does it open downwards? Down is correct. And you can tell that by looking at this coefficient in front of the leading term. The next thing I'll notice is that if I took this function and I factored out a x, I would get 2 minus x like this, right? This is f of x. So what this tells me is that this guy is going to be equal to 0 when x is equal to 0 and when x is equal to 2. So I know it's a parabola that's opening downwards. I know that at 0, it's 0, and at 2, it's also 0. It's probably going to look something like this. This is enough of a picture for me to be able to do this problem. Is there any questions about what I've said so far? Okay. Oh my God, this is terrible. I can't mean the disk method. I don't mean the washer method. So I think we're supposed to use the washer method to find the volume of the solid of revolution generated by rotating about the y-axis. So I come over here. Here's my y-axis. Step 1. Chop up parallel.
Professor?
Yeah.
Yeah, I think they're gonna say the same thing.
Yeah,
Say it.
it says shell instead of disk or washer.
Oh, good. On your version, you mean?
Yeah.
Right. I may have fixed this problem. Do I have more than one version of this worksheet? I don't. But your worksheet has it correct. That's good. That means I fixed it. And I just downloaded the wrong one to my iPad here. Perfect. Thanks. Did I? Oh man, I didn't mean washer. I meant shells. Sorry. Like I said, washer. I meant shell, obviously, because we're doing shells right now. Shell for sure. So we want to chop up parallel to the axis of rotation. So that's going to go, what color should I do it in? Green? It's going to go like this. And, you can, I don't know if this is valuable, but you could shade this part in. And then when you do that, I think you could see that it's, actually, let me write the second step. Second step is dx or dy. And when I look at this, that little bit of thickness lies on the x-axis, so that's a dx type thing, dx. And then the third thing you want to do is I'm going to set up your integral. You need to find out what the r is, and you need to find out what the height is. This is almost always the function. So I probably should have labeled the function here. The function is f of x equal to 2x minus x squared. So we set this up. The picture really tells you everything. The smallest x is going to be 0. The biggest x is going to be 2. We're going to iterate from 0 to 2, and then we stop. And we got to write the formula. In general, it's 2 pi RH. My r in this case is just those x values. My h is going to be the height of my function, 2x minus x squared. And we already decided it was dx. We put a dx at the end there. So let's do this. We got the integral from 0 to 2 pi x times 2x minus x squared dx. That's going to be equal to integral from 0 to 2 For this guy, I think you should just distribute to evaluate this integral. So one thing you could do is this whole thing is being multiplied by 2 pi. So you could pull the 2 pi out. Pull the 2 pi out like that. When we distribute the x, we get 2x squared minus x cubed dx. Now we find the antiderivative. This is going to be 2 pi times 2x cubed over 3 minus x to the 4th over 4. We're going to evaluate that from 0 to 2. So you're going to get 2 pi. You're going to get 16 over 3 minus 16 over 4 minus 0 minus 0. Take that whole thing and multiply it by 2 pi. And this is some number, units cubed. Put it in a common denominator, solve it.